quick look at a little bit of homework we had last night on 670. I want to do one of the questions for number 1. Let's go 1A, and let's do number 2 as well. Number 1A says, what's the speed of light in the following materials? We'll go with water here. I think the easiest way to do this question is to say N for water is equal to C over V for water. Right? That's the equation for the index of refraction. Now, the bad news is that's not on our data sheet, but the good news is it just comes back to the definition for index of refraction, the ratio of the speed of light in a vacuum to the speed of light in the medium. So in the end, we can derive that equation really easily from that definition if we remember the definition. Okay, let's get VW here, the speed of light in water. It ends up being the speed of light in a vacuum, C, divided by the index of refraction of water. So that's 3 times 10 to the 8 meters per second. C is always 3 times 10 to the 8. And water is 1.33. When we do the math there, I think we end up getting 2.26 times 10 to the 8. How many people did it this way? Okay, now you could actually use Snell's law for this. In fact, the definition for the index of refraction is really just a special form of Snell's law. Let's take a look at it in a slightly different way, a way that takes a little bit longer, a little bit more work to do, but allows us to do it if we forget this index of refraction equation here. Let's say V1 over V2 equals N2 over N1. That's 2 parts of Snell's law, right? So we can do this. Let's say where are we going? Let's say we're going from air to water. Okay, let's say we're going from air to water. Although we could really go from anything to water here. V1, okay, would be air, speed of light in air, which is 3 times 10 to the 8 meters per second. V2 would be the speed of light in the water, equals N2. N2 is, well, that's the index of refraction of the water. That's 1.33 over the index of refraction of air, which is 1.00. When I rearrange this, I end up getting V2 is equal to 3 times 10 to the 8 divided by 1.33. Go figure, it ends up being the exact same thing as what I just did, just a little bit longer, a little bit more roundabout way of getting there. Okay. The good news is it doesn't require you to remember an equation. This one does. The bad news is this one requires you to kind of, I don't want to say make something up, okay, but it doesn't say you're going from air to water or whatever. You could theoretically say it's going from a glass to water, okay, and you'd use the index of refraction for glass right here. For water right here and glass right here. The only problem with that would be you'd need the speed of light in glass, and we don't have the speed of light in glass. We know what the speed of light in air is already. So that's why I picked air to water, because we know the speed of light there. Okay? How many people got that right? Okay, good. Good. Number 2 says light with a wavelength of 737 nanometers. You know what? I'm going to circle that because I like to get in the habit of circling non-standard units. Although in the end, in these questions with Snell's law, because they're always ratios, every part of the equation is a ratio, it doesn't really matter what units we use as long as we're consistent. You got nanometers? That's fine. Go with nanometers. The answer you get for wavelength will be nanometers. Enters at 25 degrees. What's the angle of refraction in the wavelength? So we're going to say lambda 1 is 737 nanometers. This is the wavelength of light as it goes in. And we're going to say theta 1 is 25.0 degrees. We're looking for theta 2, and we're looking for lambda 2. Looks like we have two knowns and 2 unknowns. Wait a second here. Oh, yeah, we got something else, right? What else we got? The index of refraction for quartz glass, I think it's 1.47, isn't it? And that's going to be N2 because it enters the quartz glass. Quartz glass would be our second medium. Therefore, N1 would be 1.00. We'll just go from air to quartz glass. Again, yeah. All right, so let's say sine theta 1 over sine theta 2 equals N2 over N1. I like it when N1 is 1. I like it when we're going from air to something because that means that it's something over 1, and that term just disappears. So it becomes sine 25 degrees over sine theta 2 equals 1.42 over 1, or just 1.42. So sine theta 2, take it up by multiplying, ends up being sine 25. Take the 1.42 down by dividing. Basically, we're just swapping places, right? Theta 2 is the inverse sine of all that. So what I would do is get an answer for what's inside that brackets, sine 25 divided by 1.42. Get an answer for that. Press equals on your calculator, and then take the inverse sine of that. And when you do, it should work out to be the answer that they give us in the book here, which is 16.7 degrees. Now, our angle went down. Should our angle have gone down? Yes? Let's take a look at the wavelength of the light in the quartz glass. Now, this is easier because we don't have to deal with the inverse sign, right? We're just going to say lambda 1 over lambda 2 equals n2 over n1. One of the common mistakes that people make with this, by the way, is that people forget to go n2 over n1. They get in that habit of 1 over 2, 1 over 2, 1 over 2. Okay, it's n2 over n1. Lambda 1 is, what do we say? It was 737 nanometers. We're looking for lambda 2, and 2 was 1.42 over 1.00. So now we're going to swap places here. Lambda 2 is equal to 737 divided by 1.42. And when you do the math on that, it should work out to be 501. And because we use nanometers up here, we're going to get nanometers for our final answer. Good? Joe, did you figure out what you did wrong there? Okay. Yep. 1.47? It's amazing when we go 1.47 how we still get the same answer, 501 nanometers. I just looked at the answer. That's why we. So 737 divided by 1.42, I don't know what that is, but it's not 501. Okay. Good? Yesterday, we introduced total internal reflection. We'll spend a couple minutes reviewing that, and then we'll do another example of it. Yesterday, we used the pond and the fish at the bottom of the pond, and we determined why sometimes we can see the fish and why sometimes we can't see the fish because of total internal reflection. Today, we'll talk about diamonds and why diamonds sparkle so much and how that's related to this concept of refraction and total internal reflection. You remember that total internal reflection is that phenomenon whereby a light, when it strikes a boundary between two media, sometimes reflects as opposed to refracts. Instead of going into the medium and changing speed, changing direction, sometimes it just bounces right off of the medium. Now, that can happen in a couple of different scenarios, or a couple of different conditions have to be met for this to happen. Number one, you have to be going from a high index of refraction to a low index of refraction. You can't get it when you're going from low to high, right? If you're going from high to low, then you get that ray of light bending away from the normal line. As n goes down, theta goes up. But if you go from low to high, then you get that ray of light bending toward the normal line. It ends up going like this. And when it bends toward the normal line, when theta 2 is smaller than theta 1, you can never get total internal reflection. So unlike when you're skipping rocks from the air to the water, okay, you can't get reflection with light from air to water. You can get reflection from water to air. It's got to be from high to low index refraction instead of low to high. Now, critical angle is that minimum angle at which total internal reflection begins to occur. So if we draw this, reflection isn't occurring right there, but if we draw an angle of incidence a little bit bigger here, and we see that that refracted ray doesn't really refract, but rather skips along the boundary, that's the point at which reflection begins to occur. This angle, as measured from the normal line right here, this would be our critical angle. If we go above that, reflection occurs, and it would look something like this. If we go below that, then refraction will occur as normal. So critical angle is the point, the angle at which total internal reflection begins to occur. Now, yesterday we did the analogy, or the example, I should say, of the fish in the water. Today I want to look at a diamond here. When you buy a diamond, when you go to buy a diamond someday, or when you go to receive a diamond someday in your life, um, Ethan, I'm saying that if you want a diamond, you're probably going to have to buy it yourself. You go to buy a diamond, they're going to, depends upon where you go. If they want you to understand what you're buying, then they're probably going to tell you about four C's, the four C's when you're buying a diamond. One of them, and all of them are important in terms of the value of the diamond. One of them is color, the color of the diamond. Usually we want no color, but if there is a color, we want it to be a good color, like a deep color, because those are rare. Okay? You don't get diamonds that are colored very often, or at least like good colors very often. Sometimes they're a little yellowish. Well, you don't want that. You want no color, or you want a really good color. Um, okay, that's the first C. Second C is the clarity. So you don't want it to be a foggy diamond. You want it to be clear. You want to be able to see right through it, right? So color, the clarity. You also want carats. Carats, the size of the diamond. The bigger the diamond, obviously, the more value there is to it. Fourthly, but not least importantly at all, is the cut. The diamond has to be cut perfectly. Okay, if it's not cut perfectly, that's still going to sparkle some, but it's not going to sparkle as much. Take a look at the diamond that you see up on the board here right now. Don't worry about what these numbers are right here. Okay, it was just the best diagram of a diamond that I could find. Okay, forget about the numbers. When light comes into a diamond, it usually comes in from above, right? Usually, this is a cross section, by the way, of the diamond, right? You guys see that? And this is what every diamond is going to look like as a cross section. From above, it may be a circle, it may be square, it may be rectangular, whatever. But from the side, this is what it's going to look like. Most light comes in from above. So let's say we got a ray of light coming in from above right here. When it enters the diamond straight on, it's not going to bend. It's going to change. It's going to change speed dramatically. It's going to go down from about 3 times 10 to the 8 meters per second to about 1.2 or 1.3 times 10 to the 8 meters per second. So it slows down dramatically, but it doesn't change direction if it's going straight in. Now, if it goes in at an angle, yeah, it changes direction a bit. Let's assume that it's going straight in. That ray of light is going to go straight in and eventually hit a boundary between diamond and air. Now, diamonds have a really, really high index of refraction. And because they have a high index of refraction, they actually have a really low critical angle. And you'll see in a few minutes the calculations involving critical angles, why high index of refraction means low critical angle. Bottom line is, diamond has a high index and has a low critical angle. That means it's not all that difficult for light to exceed the critical angle in diamond. Now, it's harder in glass. Glass has a lower index of refraction, therefore a higher critical angle. Therefore, less rays of light will exceed that critical angle because the angle's got to be higher in order to exceed it. Here's theta 1. Yeah, that doesn't look like a huge angle, but in a diamond, if the diamond is cut properly, then theta 1 is bigger than the critical angle. Now, if it's not cut properly, then maybe it's not. Okay? If it's not cut properly and it's not bigger than the critical angle, then the light will leave the glass or the diamond air interface and speed up and bend away from the normal line like this. What do you see? Well, you see a boundary between the diamond and the air, because when light changes direction, you see a boundary. But if it's cut properly and theta 1 is bigger than the critical angle, then what we get is reflection, total internal reflection taking place. Now, when it reflects, goes over to this one, we get another boundary between diamond and air. If it's cut properly, and this theta over here, we'll call it theta 1 again, because it's a new problem. If this theta 1 is bigger than the critical angle, then it will reflect again. If it's smaller, then it's going to refract. So if it's cut poorly, this is what happens. If it's cut well, such that theta 1 becomes bigger than the critical angle, then this is what happens, and the light comes back out. Now, why does this sparkle more? Why does it sparkle more than if the light just went through the diamond air boundary and then left the diamond? Well, because every time light reflects, you see a sparkle. So if we shine the light in like this, we're going to see a couple sparkles sparkles right here, sparkles right here, and then the light comes right back at you right here. Whereas if the diamond is cut poorly, then we end up seeing, we see a boundary here between the air and the diamond, and then a boundary between the diamond and the air, but we don't really see a sparkle. Make sense? So it has to be cut well in order to get the sparkling, which comes from the reflection off of the boundary between the diamond and the air. Now, cut poorly, then you don't get as much reflection taking place. If it's glass or even cubic zirconium, you don't get as much reflection taking place, because the lower the index of refraction, the higher the critical angle is going to be. And if the critical angle is higher, then that means we have less chance of exceeding the critical angle, and therefore we have less reflection taking place and less sparkling. Yep. Yep. Yeah, I don't really know. Like, I don't know exactly how they would cut them now. I would guess that you're probably right, that diamonds would be better now because the technology we would have would be more likely to cut them well. But I don't know. I don't really know for sure. It makes sense though, for sure. I don't know. Well, if it's cut poorly, let's say the angle here is let's say the angle is like this. Let's say it's cut like this. Okay, make sense? Well, it's cut at the wrong angle. So it's cut right here so that the diamond is kind of short and stubby, like this. Well, now what happens? Well, look, that angle isn't as big anymore. So maybe now it doesn't exceed the critical angle because it's cut poorly. It doesn't exceed the critical angle, and the light leaves the diamond air interface and doesn't sparkle. You see the boundary because it changed direction, but it doesn't sparkle. Maybe it's cut like this. Instead of being short and stubby, maybe it's long and skinny like this, like a carrot. Yeah, the light comes in like this. Oh, look, that's going to definitely exceed the critical angle, right? You're definitely going to get reflection taking place right there, right? But then maybe, oh, wait, on this side, maybe it doesn't exceed the critical angle. So maybe you get one sparkle instead of two sparkles, right? So there is that optimum angle that you cut it at to maximize the amount of reflections taking place inside. Yep. Yeah, well, you would, yeah. Yeah. I mean, you'd have to know probably a bit more than just optics and physics, but it's kind of, okay. Let's have a look at an example on page 673. What is the critical angle for the quartz glass slash air interface? Man, we don't know anything about this question, right? Nothing given to us, except that we want to find the critical angle. Well, I'll tell you what, we do know something. We know the index of refraction of quartz glass is 1.47. That's on that table that I gave you. And air is 1.00. Now, where are we going? From glass to air or air to glass? We must be going from glass to air. We know this. How do we know that we cannot be going from air to glass? Because what? No, I don't know about the refraction angle. The index of refraction? Okay, the index of refraction, you've got to be going from high to low. Okay, you've got to be going from high to low index of refraction. You cannot get reflection taking place when you're going from low to high. It can't. So it has to be glass to air here. So we're going to say sine theta 1 over sine theta 2 equals n2 over n1. Now, what are we going to do with this? Well, sine theta 1, that's actually what we're looking for. The critical angle, the angle of incidence at which reflection begins to occur. Let me draw that picture again, in which reflection begins to occur. Right? Theta c is an angle of incidence at which reflection begins to occur. And 2 is, we're going from glass to air, so N2 is going to be 1. And then 1 is going to be 1.47. What's theta 2? When reflection begins to occur, theta 2 is what? Not 0. Somebody said it? 90. Look. It begins to occur when theta 2 is 90. So let's go sine 90. What's sine 90? 1. So it's always going to be sine theta c over 1 equals whatever my two numbers are. Theta c is the inverse sine of 1 over 1.47. Hey, let's pretend for a second I made a mistake with this and got the indices of refraction mixed up. Let's see what happens when I take the inverse sine of 1.47 divided by 1. Anybody want to take a stab at what I get? They tell you you made a mistake. If you get the index of refraction mixed up here, they tell you made a mistake by giving you an error on the calculator. Now, having said that, if you're just doing a regular Snell's law question, it doesn't tell you made a mistake. But a total internal reflection, it does. So I know that it's 1 over 1.47, so let's go back and calculate that properly now. Second function sine 1 over 1.47 gives me a critical angle of 42.9 degrees. So that's a pretty big critical angle. I think it's in the 20s, I think, for diamond. So clearly it would be easier to exceed the critical angle when it's 20-something than when it's 40-something. Right? Hence, we want that high index refraction to get the more sparkling. Yep. Rather than 1.47 over 1? Yeah, no, that's for sure. We know that it's glass to air because we have to be going from a high index refraction, 1.47 to 1.40 to 1.00. We have to be going from a high to low index refraction. If it was going from low to high, then we get a diagram that would look like this. Same angle, but notice theta 2 is smaller than theta 1. In order to get it reflecting, theta 2 has to be bigger than theta 1. If we go from high to low, then theta 2 will be bigger than theta 1. But if we go from low to high, index of refraction, then as n goes up, v goes down, theta goes down, theta 2 will be smaller than theta 1, and it can't be. You can't get reflection taking place unless theta 2 is bigger than theta 1. So you got to be going from high to low, and then it's just a matter of looking at the two media and seeing which one has the higher index of refraction. Yep.
You went low to high, did you just subtract it for the data that you got? Did that give you the actual?
No, I believe you get an error. Yeah, you do. Yeah, you do get an error. Because if we went low to high, we'd say 1.47 over 1, right? And then the calculation we tried to do a minute ago on our calculator, what we get the error for, that would happen every time. Say it again. You okay? Okay. All right. Make sense? Going to give you a couple minutes to work on page 673. One question, 3 parts. So really, it's three questions, really. See what you can do with those over the next, let's say, 5 minutes, and then we'll move on. We're going to leave you with this for homework. In addition to that, for homework, I'm going to leave you with worksheet number 17. Worksheet number 17. Now, there's a number of questions on that worksheet. I think it's a total of, let me just check here, 11 questions, my goodness. But most of the questions are pretty quick and pretty straightforward. We're going to have a quiz on refraction tomorrow. Now, your worksheet is on refraction. Please come and see me scheduled up for lunchtime tomorrow if you have questions, issues with that worksheet, so that you can be prepared for that quiz that you write tomorrow. So we're going to do that quiz tomorrow, a couple questions, and then we'll do our lab up tomorrow. So we probably won't actually be checking this worksheet tomorrow. But as I say, if you have issues with it, come and see me ahead of time. Yep.